Hello and welcome to the MOOC on optical communications. In this module we will discuss and complete the discussion of optical OFDM that we started in the last module, and then we take up some nonlinear propagation effects or propagation effects when you have nonlinear refractive index in the optical fiber. Okay. So, if you remember the block diagram for the OFDM system, that looked something like this, which we wrote at the end of the last class. So, here you had the symbols which were x0, x1, xn minus 1 corresponding to one particular OFDM frame. Okay. There are n such symbols. These symbols are of course the complex data that corresponds to the symbols. So, if it is a BPSK, then each of those x values that we have, each of those x symbols that we have would be +1 or -1. If it is QPSK, then we would have from 4 possible states and so on and so forth. These are usually arriving serially at the transmitter side, and these bits which are generated serially either from a source or from a computer are then converted into parallel form using a serial to parallel converter. So, you have a 1 to n converter over here, which then puts up the n symbols onto the parallel form. Once you have the symbols in the parallel form, the symbols are actually the data at this point, right. So, these complex data are then IFFT, that is we take a inverse Fourier transform, and after inverse Fourier transform we convert them again back into the serial data format. So, what you get at this point after the parallel to serial conversion is again the IFFT samples or the sequence of samples x of n, where n goes from 0 to n minus 1, right. So, 0, 1 all the way up to n minus 1. These are converted into a digital waveform using a DAC. Usually you will have a real part as well as an imaginary part, and in one of this type of a OFDM system, this is called as direct OFDM system, you first modulate this onto an RF carrier. Okay, so, this is an RF carrier. So, what you generate here would be the RF OFDM. Okay. So, this RF OFDM signal is further modulated on the intensity of the optical carrier and launched into the fiber. At the receiver side, you put a photodetector, convert the optical signals into electrical signals. So, what you get over here would be the RF OFDM signal, which is then sampled using an analog to digital sampler, okay, or analog to digital converter, and then converted back into a parallel form. You take the FFT of this operation. So, if everything has gone all right, then from the point where you have taken the IFFT and the point where you take the FFT, these two effects will cancel with each other, and what you get after you have converted the parallel outputs of the FFT block into serial will again be the OFDM frame x0 to xn minus 1. So, this is one possible realization of a OFDM, optical OFDM system. Okay. It is of course possible to have a slightly different type of an OFDM system, and this is called as coherent optical OFDM. Here what we do is we take the baseband OFDM signal. So, the baseband OFDM signal is the one that is produced after the digital to analog converter. Okay. So, this baseband waveform is converted into its real and imaginary components, that is you take the real part and the imaginary part separately, and then give this one to the two inputs of an optical IQ modulator. Of course, you need an optical carrier for this, which is supplied by a laser diode. The real and imaginary parts go into the I and the Q inputs of the optical IQ modulator, and what you get at the output of the optical IQ modulator will be the optical OFDM signal. Okay. So, there is no conversion intermediate into the RF domain here, rather the baseband OFDM signal is directly converted to the optical OFDM signal. This is then transmitted through the fiber. At the output, after you have amplified and then put nice band pass filters, okay, you mix the incoming signal, the optical signal, with a local oscillator signal. Okay. So, you mix it with a local oscillator signal, and then you get the real and imaginary components. Okay. You subtract or you get the real and imaginary components, which are then combined, or which are sometimes combined or does not combine. You put them through the analog to digital converters in order to generate the baseband samples. Okay. So, there is no intermediate RF conversion in this type of systems, and these are called as co-OFDM systems. This is coherent optical OFDM system. Okay. Before we talk about one additional aspect of OFDM, it might be interesting to just tell you what this OFDM stands for. in the early 80s and early 90s, in that decade, this OFDM actually stood for optical frequency division multiplexing. This is something that was not done, okay. So, in the optical domain, we do not usually do a frequency division multiplexing, or at least what we do is we not call it as frequency division multiplexing, we call this as wavelength division multiplexing, okay. So, what we have is a WDM system in the optical domain. Of course, wavelength is essentially frequency because they are related through the speed of light, but the term OFDM in optical community in the 80s and 90s meant optical frequency division multiplexing. However, after about 2006, when optical OFDM systems were started to be proposed and implemented, okay, by couple of groups in the world, OFDM stands for orthogonal frequency division multiplexing, which is what the name that is there in the wireless and RF domains, okay. So, in the wireless and RF world, OFDM means orthogonal frequency division multiplexing, whereas in the optical domain it meant once upon a time in the 80s and 90s it meant optical frequency division multiplexing. Anyway, after this caveat, let us come back to the OFDM as we have discussed in the 2 modules here. So, you might remember that when we wrote down the OFDM samples, the samples x of n that is coming out of the OFDM transmitter after the IFFT block, this x of n was the IDFT or the IFFT of the symbols xk, right. So, you had e to the power j 2 pi k n by n, where k went from 0 to n minus 1. Of course, n was also from 0 to n minus 1. There are these n samples which make up the block, correct. So, this was a discrete time version of that. If this x of n passes through the channel, let us assume that you are looking at the fiber channel, and although the fiber channel in theoretically requires an infinite number of taps or infinite number of coefficients to properly specify that, one can assume that this fiber channel, okay, for a large number of problems we can assume that this fiber optic channel itself is modeled as a FIR filter, and FIR is finite impulse response filter, and the filter length is the number of coefficients that are present in the model. So, let us assume that you have the fiber optic channel modeled as a L tap filter. So, you have h of 0 to h of L minus 1, okay. So, this is the impulse response of the fiber which has been modeled. The length here actually depends on the dispersion coefficient, and it has to be chosen in certain relationship between L and D. So, we are not going to look at this relationship, but I will develop the relationship in the problem sheet that I will give you, okay. So, for now let us assume simply that this L is large, but it is not really infinite, okay, and L is of course not really large, then you will have to wait until the samples arrive at the output, and this delay will be quite large. So, it is not too large, but it is not too small either, and whatever the length L is determined by the dispersion of the fiber, okay. So, larger the dispersion in the fiber, the larger will be the value of L. So, what would be the output of this channel when you have an input sequence x of n as input to this? Well, you might guess, right. So, initially x of 0 enters into the channel, okay. So, this is the channel, x of 0 is entering, and then you have this finite impulse response model of the channel. There has to be a convolution between the sequence h of n and the sequence x of n, right. So, that is what we would assume, and what you get at the output, let us call the output as y of 0 is equal to x of 0 into h of 0, right. So, when x of 1 enters into the channel, you now have an input sequence which is 2 bit long or 2 sample long, which is then again going through the convolution with the impulse response of the fiber h of n sequence, which is L tap filter. So, what you get is y of 1 as x of 1 h 0, okay, plus x of 0 into h of 1. The way to understand this one is to write down your h of 0, h of 1 all the way up to h of L minus 1, and then start putting in x of 1, x of 0, so on, right. So, you have this sequence that goes in like that. So, x of 1 into h of 0 plus x of 0 into h of 1. Next, as the inputs enter here, so I am sorry I took a right to left kind of a system, but you could actually take it in the other way around, does not matter. So, in the next sample when it enters, you got x of 2, you got x of 1 and x of 0. These 3 samples are entering to the fiber, right, and what you get at y of 2 will be x of 2 h of 0 plus x of 1 here, h of 1 plus x of 0 h of 2. So, you can generalize these relationships and then write that the nth sample y of n that would be coming out of the fiber, the nth sample over here where n goes from 0 to n minus 1 will be x of n h 0 plus x of n minus 1 h of 1 plus all the way up to x of n minus l minus 1, correct, times h of l minus 1. Why do we stop at h of l minus 1? Well, because the impulse response of this sequence is only L tap long, and then that would then be multiplying the L length sequence, right. So, the L length sequence that we have considered is x of n through x of n minus L minus 1. Of course, x of n minus L minus 1 can be rewritten as x of n minus L plus 1. Okay. So, this is what you are going to get, and if you look at y of n, which is the sample value at n, you see that this is actually not just equal to x of n, which is what you would have hoped to obtain, but rather there are all these terms which are coming from the previous symbols getting multiplied by the coefficients and then getting summed up. Okay. So, there is a contribution from the present sample x of n, which is what you are interested in. Okay. There is some multiplication factor that, but that is not really a big deal out of this. So, if you had y of n is equal to x of n into h of 0, that would have been the ideal case, because in that case channel would simply have been just a multiplicative channel. It would have simply multiplied by a coefficient value, and that was no big deal, right, in the sense that the samples would not have been distorted. Here the samples are now getting distorted because of the presence of all the additional terms. Okay. These additional terms which will impact the present sample, okay, is called as inter-symbol interference. Okay. So, this is called as inter-symbol interference, and this is actually an important thing in OFDM. So, you can see that this is what would have obtained. But let us actually revise our assumption a little bit, or let us revisit our assumption. Are we really correct in saying that y of 0 will be x of 0 into h of 0? Well, we will be wrong. This is not exactly correct. This is also not correct. This is also not correct. While this is true, what we must have missed in getting this generalization is that the equation that we wrote here, which is y of 0 sample is equal to x of 0 into h of 0, is strictly speaking not true. Why? Because we forgot that the OFDM symbols, you do not just have one OFDM symbol in the world, right. You actually have a current symbol. Let us call this as xc, the c standing for the current sample value. So, you have xc of 0, you have xc of 1 all the way up to xc of n minus 1. These are the current OFDM symbols, but then you have a previous symbol as well. So, you have xp of n minus 1, xp of n minus 2 all the way up to xp of 0, right. So, let us just put a boundary between the two. So, this one is the current symbol, this is the previous symbol, right. And whenever you are convolving this with the sequence h of 0, h of 1 all the way up to h of l minus 1, you have to look for the previous l minus 1 samples plus the current sample. For example, when I am looking at y of 0, my sample that will be interacting with the fiber would not just be xc of 0, it would be this one and the previous L minus 1 samples. Okay. So, there would be L minus 1 samples over here, which in addition to xc of 0 would be interacting with the fiber in order to generate y of 0, which is given by xc of 0 h of 0 plus the previous symbol xp of n minus 1 h of 1 plus all the way up to xp of n minus L minus 1. Okay. So, xp of n minus L minus 1, I suppose, yeah. So, this is xc of 0, so there are L minus 1 terms here times h of L minus 1. Okay. So, this is what you would actually see, and it is very clear that these terms which are coming from the previous sample or the previous symbol samples, right. These are the samples from the previous symbol, they are talking to the present symbol and giving rise to an ISI. I can avoid this problem of having these previous symbols talking to the present symbol or the current symbol by actually doing what is called a cyclic prefix. Okay. In the cyclic prefix, what we do is, instead of taking this xp of n minus 1 all the way up to xp of n minus l minus 1 symbols, okay, whenever your current symbol is xc of 0, instead of having these previous symbols, you replace these previous symbols by the current symbols themselves. So, you have xc of n minus 1 all the way of xc of n minus l minus 1. Okay. So, when you do this, then at the point where you are in, right. So, at the point where you are looking at xc of 0, what you get is y of 0, right. So, you can see that y of 0 has L minus 1 ISI samples, right. So, you can actually write down y of 0 as xc of 0, okay, plus. So, you can see here that when you have you have the y of 0 sample, you have previous symbol samples which are L minus 1 samples of the previous symbol contributing to the inter-symbol interference. Now, in place of the previous symbols, if you replace them with the current symbols, okay, then you can see that the sample y of 0, which earlier would have previous symbol samples ISI, will now be rewritten or will now be written as y of 0 as xc of 0 plus xc of n minus 1 h of 1 plus xc of n minus l minus 1 h of l minus 1. Look at the sample y of 1 will be xc of 1 h of 0, here there should be h of 0 here, plus xc of 0 h of 1 plus all the way up to xc of n minus l minus 2, right, h of l minus 1 and so on. If you remember your DSP, then you can DSP principles, then you see that the sequence y of n that you are generating is actually obtained by circular convolution. Okay. So, this is a circular convolution of the sequence xc of n, which is the current symbol itself, with the channel response which is h of n. Okay. So, you see that y of n is actually given by the circular convolution of xc of n. Only catch is that h of n was actually non-zero only from h of 0 to h of l minus 1. What we have done is, whenever the value here goes beyond that, we have substituted this into zeros. So, you have 0 padded, okay. So, you have 0 padded such that the length of this h of 0 sequence is equal to n, whereas the length of xc of n is also equal to n. Okay. So, while we have done this, or rather the length of this one would be equal to n plus l and the length of this one is also equal to n plus l. So, what we have done is we have equated the length of xc of n and the length of h of n together in such a way that we have made them equal lengths, and we have managed to show that the samples that are coming out of the linear fiber channel, right, or when the fiber is linear, is given by the circular convolution of xc of n with the h of n sequence of the channel itself. This h of n represents the fiber channel. Okay. Now, this is in the frequency domain, but if you take the Fourier domain or you take the FFT of this or the DFT of this, you will see that the circular convolution will in the time domain will be converted into multiplication in the frequency domain. So, what you get is y of k is equal to xc of k multiplied with h of k, right. H of k is the frequency domain transfer function of the fiber channel, xc of k is the current symbol. Since the previous symbols have all gone away and what you have is only the current symbol, we can now remove the subscript c that we were using. Okay. So, the new structure what you get will be xp of n minus 1, this is the previous symbol, okay, and then you have a sequence of L values over here, which is x of n minus 1, the current values x of n minus 1, or rather you start here with x of n minus L minus 1 all the way up to xc of n minus 1, and then you have the current symbol itself xc of 0 going all the way up to xc of n minus 1. So, this is the OFDM structure that you are now looking at. You have these as the symbol values, right. So, the length of this one is about n, and these are the complex the sample values that we had actually transmitted after the IFFT operation. The ones that we have added here, there are about L values here which we have obtained from the present symbol itself and then taken and put it back at the beginning. Okay. So, you take the last ones Okay, you have the OFDM structure, you take the last L samples, pad it onto the top or the beginning of the current symbol, right, and in that order when you do that, this is called as cyclic prefix. Okay. There is no specific thing that you have to add a cyclic prefix. You could have done the same operation, okay, by having the current symbol, which is xc of 0 to xc of n minus 1, and then taken the first L sample. So, you have xc of 0 to xc of L minus 1, as you know, or maybe the order is slightly different, I am not really very important at this point, but you could add this part, the first L samples that you have taken, and then padded it in the front of the symbol. Okay, so this would completely be the one OFDM symbol, and in this case you would have called this as cyclic suffix. Okay, it is also possible, as you might have rightly guessed, to have a prefix part, this is the symbol, followed by a suffix part. Although for operational simplicity and for general case, what we normally do is we just go for the cyclic prefix case. Okay. The cyclic prefix has an advantage. When you receive the OFDM symbols, you know that the first L samples have actually been in terms of these fellows, right. So, these first L samples are going to be in error, because this xc of n minus L minus 1 would have talked the previous values. So, this value is in the ISI, you know, is affected by the ISI. This is also affected by the ISI, right. So, these are all affected by the ISI because of the previous symbol values, and if you ignore these values, right, the only time when they do not really contribute to the ISI, the first ISI free sample is going to be the xc of 0 thing, because xc of 0 would involve only the present symbols, right, and then this would be coming out as the circular convolution. So, if this is little hazy, do not worry too much. If you ignore the first L samples of what you have received, right, which is the cyclic prefix, then the remaining samples are actually without any ISI. So, there is no ISI in these received samples. Of course, received samples will be yp, yc and y of 0, right. So, there will not be any ISI. What is the drawback of this system? The drawback of this system is that while earlier you had only n samples to send, now you have to send n plus L samples. So, when you send n plus L samples, what it means is that you are taking up that extra space, you know, of the L samples, which otherwise you would have used to send only the data. So, the effective data rate has now become n by n plus L. When L was equal to 0, the effective data rate was 1, but because L is greater than 0, the data rate has actually come down. Of course, this the ratio of L to N all depends upon the dispersion in the fiber. The larger the dispersion, the larger will be the value of L, and lower will be the throughput of the system. Okay. So, this is one of the problems. Well, with OFDM there are additional things that one has to consider when you are implementing them with the optical communication system. While optical communication system is you know, already the demand for the laser line width is pretty small, with OFDM the major impairment, there are two major impairments. One is that it is very sensitive to phase noise as well as the frequency and timing offsets. If there is a frequency offset, it shows up as a phase jitter. If there is a timing offset, it shows up as a frequency offset term. Okay. And both of these things will reduce the performance of the system. Okay. If the phase noise is pretty large, and there are many methods to mitigate those phase noise, if the phase noise is not mitigated, then it will lead to inter-carrier interference. Even the other two things, the timing offset and the frequency offset, will lead to what is called as inter-carrier interference. The details of that is not important, but this is a group of defects that will happen. The other impairment that optical OFDM systems offer is the high peak to average power ratio, because each of these symbols will be at different values and the average power will be different from the peak power. Okay. When you give such an OFDM symbol to the erbium doped fiber amplifier, the particular frequency band which has a peak value will eat up the gain of the amplifier, which will reduce the gain that is available for the other frequency bands or the other symbol or the sample points, right. So, because of this fact that the high peak to average power ratio, the amplifiers have to be designed in such a way that their linear dynamic range, the dynamic range should be very, very large, and that is not very easy to realize. Okay. And this problem of course is very severe in RF and wireless systems, not so much severe in optical communication systems, but these effects of phase noise and the timing and frequency offsets is very important. Now, phase noise you can't keep pushing the phase noise value as small as possible, because phase noise depends on two factors, right. One, you have the line width delta nu of the laser, and there is only so much you can do to minimize the line width. If you start putting the line width value, require the line width value to be very small and small, then the expense associated with the laser also starts going up. Okay. And the other thing is that it depends on the bit rate. The phase noise variance depends on the bit rate and is usually inversely proportional to the bit rate, and nevertheless you can't keep simply increasing the bit rate. There are problems with increasing the bit rates later on, right. So you can't simply say, okay, the phase noise variance might be low at 1 terabit per second, so why not run the OFDM system at 1 terabit per second? The answer is not so simple, because if you run the system at 1 terabit per second, while the phase noise term can be reduced, there are a whole lot of other problems that will throw up, right. So how do you receive the signal, how do you sample the signal, are there any are there enough things at the electronic side, at the DSP side, to mitigate all the other factors? So there are a lot of things that will go wrong when you simply try to increase the data rate, and that would again of course not be possible. So there are methods people have developed in order to overcome all this. Perhaps that would be the discussion for a different module and a different course altogether. So we will stop here and continue with the fiber effects in the next module. Thank you very much.